So having introduced parity-check codes as a way of randomly constructing linear codes, we have seen that the weight enumerator, the average weight enumerator, leads to a minimum distance that's growing linearly with the length n. So they are quite good codes. They have favorable error correction properties. Now we're going to look at the maximum likelihood decoding performance. Because maximum likelihood decoding performance is hard to analyze, we focus on one channel where maximum likelihood decoding can actually be implemented in practice and where it can actually be implemented quite easily. And that's the MAP decoder, maximum likelihood decoder binary erasure channel. So in general, we know that MAP or maximum likelihood decoding is infeasible because the complexity is exponential in the length of the code. But on the binary erasure channel, complexity can be reduced. And it turns out that maximum likelihood decoding or MAP decoding is actually relatively simple on the binary erasure channel. And later, the binary erasure channel will also help us to simplify the analysis. And also historically, the LDPC codes that are the core of this chapter, initially they have been introduced for the binary erasure channel for packet networks. And today, still, the binary erasure channel is the first step into analyzing new schemes because of its simplicity. And then later you port everything to more complicated channels. So we start with the MAP decoding. And for this, we start with a code that is defined by a parity-check matrix. It can be a random parity-check matrix. It can be any parity-check matrix. The code construction doesn't matter. We just need to have the parity-check matrix. Then we assume that the transmitter chooses a code word X and the transmission takes place over the binary erasure channel. The received code word Y has elements that are 0, 1, or an erasure. Question mark marks an erasure. And we denote the index set of the erasures with the set E. So the set E is the positions in the received code word where we have an erasure. So assume, for instance, we have received a code word Y, which is 1, 0, erasure, erasure, 1, 1, erasure, 0. And that means the erasure set E is equal to 3, 4, and 7. Because we have an erasure in the third position, we have an erasure in the fourth position, and we have an erasure in the seventh position. So and that's the erasure set. So E is the index set of erasures. And it's essentially the set where Y of i's, where Yi is equal to a question mark. Then we denote E bar to be the set of correctly received bits. In this case, E bar is equal to 1, 2, we have erasures in 3 and 4, then we have 5, 6, and 8. So the positions 1, 2, 5, 6, and 8, they are correctly received, and therefore they are being put in the set E bar. Okay, so now what we do is we take our parity check matrix and we split our parity check matrix. So we take the columns that correspond to the erased positions and we put those in the matrix HE. HE is the submatrix consisting of the columns of H where the index I is an element of E. So recall every column of the parity check matrix H corresponds to one position in the code word or received word. So every column corresponds to one position in the code word. So what we do is we extract the code words where the index is an erasure and we put this in the submatrix HE. So then we also define the vector xe to be the vector of the code word consisting of those elements where the index is an element of E. So it's essentially the subvector that corresponds to the erased positions. Essentially, this is what we don't know. This is what we need to find out during decoding. That's xe. Okay, then we continue. So we look at an example first. So here's another example. We have a parity check matrix H, and we have a received vector Y with erasures in the second, fourth, and fifth position. And the set E bar is then the set of correctly received positions 1, 3, 6, and 7. So what we do is we take the columns corresponding to the erasure, so the second, the fourth, and the fifth, and we put them in HE. So HE corresponds to the second column of H, the fourth column of H, and the fifth column of H. That is what we put in HE. And in HE bar, we put the correctly received columns. And these are columns 1, 3, 6, and 7. So that gives us HE and HE bar. Now with HE and HE bar, we can formulate a system of equations as follows. So we start with the maxima posteriori rule. So the MAP rule is that x hat is the code word x that maximizes p of x given y. Now we need to maximize over all possible code words. How do we define what is a code word? So we start here because this is easy. P of x given y is something that we can calculate. The difficult part is the x being a code word. How do we define which x is a code word? Well, by the definition of a linear code. So h times x transposed is equal to 0. And now we know that we can use our separation of h into he and he bar to formulate this equation. So this equation is the same as he times xe transposed plus he bar times xe bar transposed. Must be equal to 0. Recall, if we say h times x transposed, what we do is we pick the first column of h multiplied with x1, second column of h multiplied with x2, third column of h multiplied with x3, and so on. And then we sum up everything together. So we can rearrange the order of the summations by first doing he times xe1, he1 times xe1. So we just look at the ones that correspond to the erased positions. And then we take the ones that correspond to the unerased positions into he bar times xe bar transposed. So that is how we separate this. So this sum, if h, we can also write this as follows. So if h is equal to h1 transposed, h2 transposed, up to hn transposed, this is equal to, so h times x transposed equals to 0, is equivalent to saying that we have h1 transposed times x, so h1 transpose times x1 times x1 plus, these are vectors, times h2 transpose, these are column vectors. So recall that we always calculate with row vectors, so these are column vectors. So h2 transpose times x2 plus hn transpose times xn equals 0. So now we take this summation and we divide this into some erased positions and some unerased positions. And we just group them differently, and then we get HE times XE transposed plus HE bar times XE bar transposed equals to 0. Now we can rearrange this. We can put this guy on the other side of the equation. We're working with binary numbers, so plus and minus are the same. So we get HE times XE transposed is equal to HE bar times XE bar transposed. We know XE bar transposed. Why do we know XE bar transposed? Because we have Y. We have Y, and this corresponds to the unerased positions of Y. The binary erasure channel never makes an error. It just erases. There are no errors. So what we can do is we can just take Y at the unerased positions, and we know this is XE transposed. So this is actually something that we know. Make it red. This is something that we know, and this is something that we can define to be S transposed. So we define S transposed equal to HE bar times XE bar transposed. This is the syndrome, something like a syndrome. This is something we know. And then we have a system of equations. So we are left with this equation or this system of equations. So HE times XE bar times XE transposed must be equal to ST. We know ST, we have calculated ST. We know the parity check matrix HE. So we have an unknown that is XT. So we know that X should be a valid code word. So we must have a solution. But we also know that the rank of HE is upper bounded by the number of erasures. So if the rank of HE is equal to the number of erasures, then we have a unique solution of the system of equations. Then we can recover XE and we can solve the system of equations. Rank is equal to epsilon. We can recover XE by solving the system of equations. So if this matrix HE has rank of number of erasures, solve the system of equations, for instance, using Gaussian elimination or your favorite system of equations solver, and then you get XE. So then, on the other hand, if we have multiple solutions, if the rank of HE is smaller than the number of erasures, then we have an underdetermined system of equations and we have multiple solutions. So we can group all those solutions in a set XMAP. So XMAP are all the code words from C such that HE times XE transposed is equal to S transposed. So this is S transposed. This is equal to S transpose. And XE bar is equal to YE bar. So this is essentially the set of all code words. And we say they are compatible with the received Y. Because if we receive Y, then we can look at which code words fulfill this equation, this one, and these are compatible with Y. Now we need to choose one of those. We need to choose one that has the highest probability or likelihood or a posteriori probability. That's what we're going to do next. So first, we assume that X is uniformly distributed and each possible code word occurs with probability 2 power minus k. This is a usual assumption. This is the assumption that we also do here. Then we apply Bayes' theorem, our usual friend. So we can calculate P of X given Y is equal to P of Y given X divided by P of Y divided by P of X, or times P of X, and P of X is 2 power minus k. So we insert this and we divide by 2 power k. And then we have the usual maximum likelihood solution. So the MAP solution, y is equal to the maximum likelihood approach. So it's the maximum over all x prime of the code words of P of y given x prime. So now we look at the code words that over which we maximize. So if x prime in the unerased positions is different from y e prime, then this can never happen. So we can never get an x at an unerased position that's different from y. So in that case, P of y given x prime is equal to 0. So on the other hand now, if x prime at the unerased positions is equal to y at the unerased positions, then we have E cardinality erasures, and P of y given x prime is 1 minus epsilon or n minus cardinality of E, the probability that we have no erasures. Probability 1 minus epsilon, we have no erasures, and at cardinality of E positions, we have epsilon erasures. And this probability only depends on E and not on x prime. So let's take a look. So what this means, we have this set of compatible code words. And they are all equally likely. And the transmitted vector is either determined by y, or we have multiple solutions. So either we have a single vector in this set of compatible vectors, then we can choose it. But if we have multiple solutions, we don't know which code word is the best because they have the same likelihood. So we cannot decide. So only what we can do is we can say that x MAP of y is the 1x. This should be a bold x from the set x MAP. If the cardinality of this set of compatible words is equal to 1, and otherwise we need to give back a decoding failure because we cannot decide. It could be 1. We could randomly select the code word, but it makes more sense to tell the receiver, look, I cannot decide. It's just not possible to decide. So can take a look at the example that we had. So we had this example with 3 erasures, a parity-check matrix, and we have S transposed is equal to H E bar times X E bar transposed. So that's something we can actually calculate. And we get our vector S. Then we have a system of equations. So we have a system of equations, HE times XE transpose is equal to S transpose. This guy looks already good because we have 3 unknowns. We have 3 equations. So there is some hope that we can fulfill it. And if we look at this matrix, we also see it has full rank. It has rank 3. You can look at it a little bit closer, but you can also either do Gaussian elimination to determine the rank. And we can essentially solve the system of equation first using the last equations. We get xe2 is equal to 1. Last equation, xe2 is equal to 1. Then we go to the second equation, which says that xe1 plus xe2 is equal to 1. So that means that xe1 must be equal to 0. Finally, the first row, xe1 plus xe3 should be equal to 0. And that gives us xe3 should be equal to 0. So we get our erased positions. We can also do it using matrix inversion, and then we can also calculate xe. So this is MAP decoding. This is blockwise MAP decoding, and that's essentially the way how to do the decoding. I will also put a MATLAB script on the GitHub server to illustrate this further. I don't have a reference on the slide yet, but I just decided that something I can quickly do on the fly and upload this to GitHub as well. So quick note about complexity. So we have the maximum likelihood solution if we assume uniform priors. The complexity is n cubed because we must invert HE, and inverting a matrix or solving a system of equations can be done using Gaussian elimination. And we know that the complexity of Gaussian elimination is cubic in the size of the matrix. This is not as bad as e to the power n or 2 to the power n, which is exponential in n. This is polynomial. This is n cubed. This is okay. So there are some applications where this is actually feasible and where this is actually being done. If the number of erasures are small, then this matrix is small and inverting is not so bad. However, we would also like to have something simpler that is not cubic in n, but linear in n. Especially if we have big codes, then we want to have some smaller complexity, because if n gets large, this term also gets very, very large. But MAP decoding is actually feasible, and we can do MAP decoding to get an upper bound on the performance. So let's take a look at a variant of MAP decoding, which is the bitwise MAP decoder. So far, our MAP decoder is a blockwise MAP decoder. So what do we do so far? So far, we want to have a vector x hat, which is the code word that maximizes the a posteriori probability P of x given y in terms of vectors. This minimizes the error probability of the whole code word. Now we would like to minimize the error probability of each bit. So we can define the bitwise MAP rule. So that's the bitwise MAP decoding rule. And that is this one. So we make for each bit xi, we're looking at bit at position I, we maximize the a posteriori probability of this bit being either 0 or 1 given y. We don't need to maximize over all the code words, but just over this bit 0 and 1, and we have the a posteriori probability of xi given y. It looks to be very simple. It will turn out that it's not so simple. So let's take a closer look. So first, if I is not erased, we immediately have xi, because xi is just equal to yi. That's the no-brainer. The interesting case is if I is erased. So when can we recover xi? So actually, it turns out that we still need to do the Gaussian elimination. We still need to calculate this set of feasible or compatible vectors, compatible code words. And then if all the xi have the same, if all the vectors in this compatible code words have the same value for the ith bit, then we can determine this bit. So formally, we can write this. So we have the maximum over alpha being equal in 0, element of 0 and 1, P of xi given y. And now we marginalize over all possible patterns x, where xi is equal to alpha. Then we have P of x given y. And here then we can say P of x given y. We need only to sum over all possible code words. Because otherwise, P of x given y is equal to 0 if we don't have a code word. So we sum over all the code words x, where xi is equal to alpha, P of x given y. And this is equal to alpha if all x in the set of compatible vectors have an alpha in position I. And otherwise, we need to put an erasure. So again, we need to calculate this set x. So this is actually computation of this set x MAP. And this set x MAP involves a matrix inversion. Now, practical LDPC codes, they have sizes ranging from 10,000 to 100,000 quickly. So the complexity n cube can often not be used, and therefore we need to resort to different algorithms. So what we need is simple algorithms, and that's something we're getting to later in this chapter. So now we're looking at the performance of maximum likelihood decoding on the binary erasure channel. We can actually calculate the maximum likelihood decoding performance. And what we do is we calculate the average error probability averaged over all possible random parity check matrices. So instead of looking at one specific code, again, we're looking at the average performance of a randomly constructed parity check matrix. So we take the expectation of the error probability, and the expectation is over all the parity check matrices. So it's a set of matrices. This is kind of a sloppy notation. All the matrices that are of size m times n, where the probability of hij is equal to 1 is equal to 1/2. Set of all randomly constructed parity check matrices. So how do we do this? Well, we don't prove it. Again, it's a very lengthy and technical proof. And I refer again to the supplementary material for the proof. But it turns out that the average error probability is given by this expression. Essentially, it's nothing else as calculating the probability that this matrix HE has full rank. If you look closely, you will recognize this term. This was in the very first lemma of this chapter. We calculated the number of full rank matrices, exactly this term. So we calculate the probability that this matrix HE has not full rank, and then we cannot decode. Or we calculate the probability if we have more than m erasures. If we have more than m erasures, we don't have enough equations to invert the matrix. Then we have an overdetermined system of equations. We have more equations than unknowns, and we cannot solve a system of equations. So this is the second case. So if we have more than m erasures, then we cannot solve our system of equations. What I said before was wrong. We have more unknowns than equations. So it's not as I said before. We have more unknowns than equations. There is no chance that we can solve the system of equations. And it may also happen that we cannot invert the matrix HE because it's not of full rank. So it's this rather unpleasant expression, again with a lot of binomial coefficients. And we can find a very simple upper bound. That's this guy here, this upper bound. So it has n plus 1 to the power 2 minus n times d2. And d2 is given by this expression. That's an abbreviation for the Kullback-Leibler distance for binary random variables. Again, the proving this term is not so difficult. That's what I just said. So just counting the possibility that we cannot invert the matrix, either because HE is not a full rank or because we have too many unknowns. Then getting from this expression to this simplified upper bound, that's a little bit more tedious and technical. So that's in the supplementary material. So let's take a look at the implications of this. So this is a big plot, a lot of curves, but let's go there step by step. So first, we have a code of rate 1/2. And what we plot here is the average error probability under map decoding for different lengths of our code. And we plot the exact expression and the upper bound that we calculated. We see for n equals 50, the exact expression is not very nice. So we have here is the erasure probability. We know that for rate 1/2, the capacity of the binary erasure channel is 1 minus epsilon. So it has a capacity of 1/2. And what we see here is for n equals 50, we are very far away from this performance. With an erasure probability of 1/4, we have an error probability of 10⁻³ roughly. And the upper bound is quite loose and quite far away. For n equals 100, the performance gets better. The upper bound also decreases, but still not very nice. And for n equals 1000, now we see very nice behavior of the curve. So it decreases rapidly. The error probability goes to 10⁻15 already for an erasure probability of 0.37. And the upper bound also decreases similarly. Now, if we further increase n, calculating this exact expression becomes tedious because the binomial coefficients that we have in the expression, they grow tremendously. You can use libraries with have support for very big numbers, but they tend to get slow. So what we do is we're just looking at the upper bound. So how does the upper bound behave? That's the dashed curves. And again, apologies for my PDF program not being able to display dashed curves in a consistent way. If you open the PDF of the slides with a different program, you should see them correctly. So this is the upper bound. And we see if we increase n further, the upper bound becomes almost like a vertical line, and it approaches the capacity. And with n equals 50,000, the upper bound already is very close to capacity. And seeing that the upper bound is quite loose, we expect that the true performance is somewhere over here. And even the upper bound will converge to the capacity. So if we increase n, then this upper bound here, this will dominate and this will go to 0. So this term actually will converge to 0 if we increase n, and if epsilon, or if the rate is smaller than 1 minus epsilon. This is a condition. So if the rate is smaller than 1 minus epsilon, this guy will go to 0. So essentially we have codes that are capacity achieving. So with MAP decoding with complexity n cube, we can achieve the capacity with a linear code because the error probability gets to 0 very fast if we increase the length n of our code. That's the main takeaway of this chapter. So that's our introduction to parity check codes. Now, in the next video, we're going to introduce low density.